Hello, thank you for coming, and I'm very glad that you're here and you still want to learn about mesh shaders. You don't have enough. My name is Łukasz Izdebski, and I am developer technology engineer at AMD. And today I want to talk about mesh shaders and work graphs. I'm very glad that this year at this conference that this topic is very popular, and I hope that you attend both of those meetings. And Eric and Radosław had a very good presentation about it. Yes, so yeah, my presentation, I want to take a different path, and I will not show any shader code, so no code will include it, but I want to just show off what this technology can do, and learn it, just show off it how is what is capable, and etc. and show it examples of usage. Yeah, but I will just do a very short, brief introduction of mesh shaders technology, and okay, so before mesh shaders, the graphic pipeline was looking as on the top. As you can see, it contains a lot of stages, and we can divide those stages up to one. There is a programmable ones, and there's a stages that are just convertible. So you cannot write a program for that. Just you can convertible. So, but GPU hardware overcome the huge evolution over the years, and right now this pipeline doesn't resembles the hardware, GPU hardware. So this is why the mesh shader was introduced, and as you can see that mesh shader pipeline is looking different, and they dropped a lot of those stages before rasterization and introduced only two. Programmable. So one is mandatory, which is mesh shader, and one is optional, which is amplification shader. One thing I just want to show that we are missing the input assembly stage on the mesh shader pipeline, and this will have consequences, and I will talk about it later. When you are working and you're learning about mesh shaders, you will see that they are very similar with the compute shaders, and in both cases you need to think about it when you work with them. You need to thinking about threads, about thread sizes, work group sizes, and everything else. So, but mesh shaders can do a little bit more than compute shaders. They can exporting vertex data, vertex attributes to the graphical pipeline. And the same with the primitive connectivity, like vertex indices. So mesh shaders can interact with graphical pipeline of GPU. So the first consequences of lacking of inputs and assembly, that we cannot introduce to this pipeline the same data as we're doing to the traditional pipeline. So we need to split the mesh on smaller batches, and those batches are called meshlets. And there's you can create meshlets as you wish. There's no one way. There's a standard of that. You can create the meshlets that they are more fitted for your usage. And so it is very similar with the story with the memory management with what we have with the DirectX 12 and Vulkan. But you can to ease this pain of memory management, there are libraries on the net. For example, DirectX 12 or Vulkan memory allocator developed by Adam Sawicki. The same story is with the mesh shaders. On the internet, you can use application that will create meshlets for you. And those meshlets will be probably the best suited meshlets for your usage. But as I said, meshlets is not end of the story. You can create meshlets as you wish, and they are when you create it, your data, so you can create meshlets as best fitted for you. When the meshlets were introduced, extension of all techniques are the pop-up first, because we're not dealing with whole mesh at once. We are just working with smaller patches of those meshes, so we can do more fine-grained things like calling or loading. So we can call on the meshlet level, not on the mesh level. But this is the end of the story. Our colleagues from AMD, with collaboration with Coburg University, came up with the meshlet mesh shader compression technique. And they use, because we are dealing now with on meshlet level, so we are dealing with smaller patches of whole mesh. So for example, we don't need anymore the 16 bits or 32 bits of data for storing for indices for the mesh. We can use smaller number of bits. And by doing that, we can save, 4 times memory for that. And with additional quantization tricks, we can go even further. But as I said, I will not go into details. Everything will be described in our blog post site. It's not yet ready yet, but keep us following us on the X, on different platforms, and we're gonna notify you when this blog post will be published. I will not describe it how we did it, but I just want to show off the results. So as you see that we can gain a lot of compression when using this technique. And what is important, the compression is done inside the mesh shaders. So we don't need any decompression tricks before rendering to use this compression algorithm that we developed. And as you can see that using the compression data, we are, and when we're rendering Lucy or Rock, we can see that we are even a little bit faster than when we are rendering those models using a traditional pipeline. When we drop the compression thing and just render those models using mesh shaders, you can see we are approximately 20% faster. But when we, on top of that, we use those calling things that was, for example, Eric mentioned, we can gain a little bit even more, but only on those models that contains front-facing and back-facing meshlets. For example, Rock is not contain those things, so we gain almost nothing. But the second consequences when not having input assembly, we not longer limited for the primitives that are which input assembly can have. For example, I'm talking about triangles, triangle strips, lines, etc. We can create our models with different type of topologies. For example, quad-based mesh. Quads are very popular on the modeling stage. They are very popular because with their properties is the pain of modeling, and but unfortunately hardware today doesn't support rendering and interpolated of attributes using quads. And on some stage, those quads need to be split on two triangles. But when we do that, unfortunately, those artifacts can appear, and so this is C1 discontinuities of interpolative attributes. And what we want, we're dealing with quads. We want to have different kind of. For example, we want to have a bilinear interpolation. This is even more visible when we are dealing with animation, and those artifacts are more visible, and so. What can be done right now? We can hide this problem, and we use highly subdivided surfaces. And this problem will still occur, but will be very not visible. But another thing what we can do is to trick somehow the hardware and do bilinear interpolation over our quad. And this can be done using with a little bit of math, but you can ask me if the solution for that is just a little bit of math. So maybe it can be used on the traditional pipeline, and the answer is yes, you can do that, but unfortunately there's a gray graph underneath. But when you but the mesh shaders are most suitable for that, and they are the fastest way of rendering quads using bilinear interpolation. Yeah, sorry about that, it's not gray here, but yeah. But additional things, this is not over. Okay, our colleagues, once again from IMD with the collaboration with Coburg University, came up the technique that using mesh shaders, we can do subdivision surfaces techniques, for example, Cladmore-Clark subdivision, and yeah, so we don't need a tessellator anymore. We can do everything using mesh shaders, and their approach is very robust and can handle even those not pretty, situation, highlight in red, orange, and blue. So if you're interested in that, I just encourage you go and download their paper and read it. But this is not it. Mesh shaders can do even procedural geometry, so we don't need any input for the mesh shaders. A mesh shader can create on-fly geometry. And for example, our colleagues we rendered those grass patch using created procedurally inside the mesh shader, and we can, on top of that, we can do even some simple animation, procedural animation on top of that. But why stop there? Why we don't? On top of that, we can use the amplification shader. And when we give the amplification shader the height map, so we can spawn those batches of grass more strategically and use height for the spawning those grass. And the result is what you see right now on the screen. This foliage is rendering all using this what I mentioned, this technique, using amplification shader and mesh shader. How we did it? So this time, this blog post is available on our GPU open site. So I encourage you, if you're interested, go and read it. But mesh shaders is not only technique that I want to talk today about. Let's focus now on the future of GPU programming, and I want to talk a little bit about work graphs. Work graphs is a multi-year collaboration between Microsoft and industry partners, and this year, before GDC, the specification of work graphs 1.0 was released. I will not explain it in much detail, this work graphs, because I will probably need another hour to do so. But I'm encourage you go, if you're interested on those things about work graphs, go and read the blog post about it. I will just do very short introduction of work graphs. Yeah, so in one way you can think about work graphs as an evolution of technique that was introduced to the DirectX 12. It is execute indirect, and so when you want to push as much work to the GPU and we don't want to have a much interaction with CPU, the execute indirect was developed for that. And so, for example, when you do some kind of classification, you want to classify something on the scene, and dependent on the type of thing that you classify, the consumer will consume only those data. You can implement this technique using execute indirect, but eventually, when you do that, you can introduce the performance overhead, because, for example, something that is now you classify and looking for circles, and the circle is not present on the scene, you can introduce the performance overhead because of wasted length. But the worst, you can even introduce the memory overhead, because every consumer needs to be prepared for the worst case scenario for all those supported types that you will classify. So you can introduce a lot of wasted memory when implementing this thing with using execute indirect. So, in a nutshell, the work graphs are you writing a node. Node can be written using compute shader, and every node is connected by edges to another node, and every node you can figure out that contains a virtual queue that when this node create, you can create some data and put it to the virtual queue, and when the GPU, the scheduler, decides that you created enough work, the GPU will spawn and execute the work for the next node. So in other way, you can say that this is a way how to expose and the program that the GPU create work for itself. We don't any need for the CPU intervention, syncing, etc. So in other words, you can think about it as work graphs is a data flow model. When the data are coming to the node, is executing, transform it, for example, and the node can create work for the child node. And when you queue it to this virtual queue, the GPU itself will decide for you when to launch the next node in the work graph. So with work graphs, the new opportunities arrive, because nodes can, for example, be used in the recursive algorithms, and with some restrictions, each node can launch itself, and so we can try to do some kind of syntraversal techniques can be developed using work graphs. Additionally, the work graphs are very suitable for developing the adaptive algorithms. When you, for example, want to do some kind of physics simulation and you divide the world to the cells, the work graphs can, adaptively manage more work on those cells that are needed to compare it to those nodes where they are sparse and there are less happening in those cells. The same story is with the long execution chains. So, for example, when you do some kind of screen space reflection, very often is that when you spawn those pixels, work for those pixels, a lot of those pixels are finished very earlier compared to different ones. So, yeah, you need, but in the traditional way, you need to wait for those all pixels to finish. And so, yeah, the work graphs can better low balancing thing and can go further with. So work graphs can spawn the next pass, even if some in a different region is doing the previous step. Okay, so until now I was talking about work graphs in specification 1.0, where the nodes can be written using only compute shaders, so we can interact only with the compute queue. And now I want to present the preview feature of work graphs. And now work graphs nodes in node graphs can be written as a mesh shader. So in other way, you can think about it that work graphs with mesh shaders are the amplification shader on steroids, because you can do much more with work graphs with the mesh shaders. And once again, our colleagues with collaboration with Corbeck University came up for demo of this feature and what we called procedural enhancement. So for now, we just show the screen of what they did. And at the demo, not all those things were rendered using work graphs and mesh shaders, but we enhanced the quality, visibility quality of this demo. And let me demonstrate it on three areas. First, I want to talk about Meadow example. So in here, we extend this technique of rendering grass. And mesh shaders now lets us not only render grass with this technique, but for example, when we do classification and when we want to spawn, we decide what to spawn, we can try to test if this batch of land is in the sun, so we can draw grass patch on that. But when we are in the cave, for example, we don't want to grass, we want to spawn the mushrooms in there. So, but in addition, we can do a little bit more. So, for example, we can decide that we want to draw the flowers on top of the grass. And what that's not over. We can even, when we spawn flower, we can decide that we want to add those bees, this animation and bees, and for example butterflies. And all this thing was done by using dispatching one dispatch of work graph. So node execute indirect was needed, and I was mentioned all those things was procedurally generated inside mesh shader. So those bees, those animations, all those meshes was created, inside the mesh shaders. This can be done the same with when we're working with work graphs, but yeah, so we can do this classification error. But to spawn and render those meshes, we need to execute from the CPU side the execute indirect. So for this reason, work graphs are better, less CPU GPU interaction. The next part of our demo was to enhance the add on top of render on top of the geometry those ivy leaves, and it's with work graphs to create such thing is very easy, much easier than doing the same with different approaches, because as I said that we can in work graphs we can do recursive algorithms, so node can call itself, and yeah, so we can by that we can decide how long this ivy chain will be, and we can add a little bit logic to terminate early or even fork. So yeah, so once again, all those three was created dynamically. And the last part of our enrichment procedure was rendering this marketplace example. Yeah, so all those things you can see was generated and rendered using work graphs. How we did it? So this is a more complex part, and it contains five stages. And let me talk about it, how we did it step by step. Okay, first, as an input of our work graphs, we from the user we get the area where the user want to spawn the market. Then we recursively subdivide it on the for the islands, that the size of the islands we want to have. Oh, sorry, it's not visible. Oh, sorry about this gray thing. Okay, but yeah. So when we do it, so between islands, the node is creating the paths between the islands, and it's even interacting with the road outside our initial area. Okay, so inside the islands we spawn procedurally the stalls, and yeah, we even play with the material of each stall. Then we even are available can enrich this thing even more and try to connect stalls between islands using grasslands, rendering grasslands. Yeah, and as a cherry on the top, we introduce props inside the islands, and not only inside islands. And depending on the position, or how much size we have available, we can spawn a different type of prop. Okay, so a little bit stats about the demo we created. So it contains 37 nodes. 9 of them were mesh shaders. We use approximately 170 megabytes of memory, and the number of payloads was around 200,000. And it could become, you can think about it that it contains 3,000. Over 2,000 raw calls per frame, and it was contain about 30 million of triangles per frame. And what I want to say that we run and compute and procedurally enrich these things every frame. There was everything was dynamically rendered, so it was not pre-baked or statically calculated before. No, everything was run every frame dynamically. Maybe I can even. What time? How much I have time now? So, but I think I have still time. I just want to maybe show some. Okay, so I even have time. So I've prepared some. Unfortunately, I cannot run this demo on this laptop, but I create some videos to show it. So yeah, this. As you can see that, yeah, so I focus on this meadow, and I will see that what was rendered using word graphs or not. Yeah, and the next one. Yeah, sorry, I will fix it. Now it's moving to this ivy. Ah, sorry. Okay, sorry guys. Yeah, let's. I need to put. Okay, but do you see? Did you see the previous one? No. Okay. So sorry. Give me. It's not easy to. Oh yeah. Yeah. So as you can see that I just enabled the rendering of word graphs, and yeah, now we'll just show off what was rendering using word graphs at this part. The second part is. Yeah, let's go and show off the bridge, the Ivy part. Yeah, so this is yeah, rendering. Oh, well, it's very close, very short. Okay, now I'm playing about how many iteration I used with rendering those Ivy. Maybe I will show it again. Yeah. So, as I mentioned, everything was dynamically rendered. Okay, and I will go to the market. And yeah, and as see as a market, it's the step by step how we render it, and I will just show that yeah, it's as an input of this. Of word graph, I just play around the area size of the market, and yeah, showing that everything was dynamically rendered frame by frame. Oh, yeah, then you can even see play with the size. Yeah. Okay. I want to thank Lou, Max, and Matthias for helping me with the presentation. And yeah, for now it's all. And yeah, thank you for attending.
Hi, Łukasz. Thank you for the talk. I have a question regarding the procedural part. So I guess you can argue you can pre-generate that and then transfer this geometry like vertex buffer and render it directly. So the question is, have you made a case study where you would compare the static geometry versus mesh shader for the procedurally generated content? Thank you.
Yeah, thank you. That's everything was shown is a work in progress, so we didn't have any time to compare it. We just want to extend the capabilities of word graphs, and we are focusing now on the extend the capabilities of word graphs and mesh shaders.
Thank you.
Thank you for the presentation. Got a quick question. What's the status of the debugging tools for the word graphs?
Work in progress.
Thank you. And do you know what is the ETA? Like if it's coming this year or maybe next?
I need to say tomato on that.
Hey, so one thing I like is that the programming model you're showing actually makes it easier for a programmer to write the code to spawn all these things, right?
Yep.
But technically, it's also possible with compute shaders always, right?
Yep.
In the end, it might be harder to program, more annoying to maintain, and so on, right? But when it comes to porting existing content to mesh shaders, yeah, I'm just wondering, what are the trade-offs? Like, for example, the communication between the newly spawned tasks. How does it work? Is it LDS or is it GDS? Are there limitations? Like, does it have to be spawned on the same workgroup or compute unit? This type of stuff.
Oh, okay, it's very detailed, and I would say this. It isn't end of the story. No, we are just developing that, and so everything can change. Even if I can answer you right now, but it could change in another version of the driver. So it's
Right. So this communication will be driver dependent, right? So new generation of GPUs comes, and there will be completely different performance
it could be.
trade-offs.
So this is why I cannot
Okay.
answer directly.
Okay. Yeah. Thank you.
Hey, thanks for the talk. Perhaps this was covered by some earlier presentations, but I just wanted to ask, like, how much hardware does support this nowadays? I mean, because this is probably just a new approach to the graphics pipeline, right? So this is probably just supported by the latest hardware, or is it not supported at all today, and you're just showing something of the research potential?
No, the demo was running on I think the Arduino 3, but for the mesh shaders is Arduino 2, but the work graphs. I will double check. I don't remember right now. It's Arduino 2 or 3.
Okay.
Limited.
Okay, thanks.
Okay, but at the end, just I want to encourage you guys, experiment with mesh shaders, and when the workgraphs will be available, just experiment with them too. And I hope that in the next Digital Dragons you will have a presentation about your outcome of your experiments, what you did with the mesh shaders and workgraphs. Okay, looking forward for that.